Hello everyone, my name is Wang and I come from Chinese Academy of Science. Today I will introduce our paper, which focuses on automated Heap Feng Shui. In the first part, I will introduce the motivation of this paper. First of all, I want to say that AEG is very important because the numbers of vulnerabilities growing very quickly. And so we need to evaluate the exploitability of the vulnerabilities very quickly so that we can give a priority of the vulnerabilities. So we need the AEG to generate the exploits. To generate a working exploit is very for the complex vulnerabilities. We especially the vulnerabilities on heap. Automated heap Feng Shui is needed. It is because that the vulnerabilities on the on heap can only be exploited in a specific heap layout. For example, heap overflow vulnerability, an exploitable object should be placed at a position which is next to the overflowed object, so the sensitive pointers in the exploitable object can be controlled. Generating a working exploit is very complex process, and there are many challenges. In this paper, our solution, which we call it Maze, is only focused on memory layout manipulation, which means that the input maze is a POC and an expected memory layout. In the second part, I will introduce the overview of maze using an example. In this example, there is a UF vulnerability. You can see that the delete switch function did not clear the pointer to exploit the UF vulnerability. The expected layout is placing controllable objects at the free object switch so that the sensitive pointer in the freed object can be controlled and creating arbitrary memory rights primitive. First of all, we need to analyze and extract the heap layout primitives from the program. In this example, the primitives are code snippets in a function dispatcher, and the switch case structure in this example is a function dispatcher. And the create router, create switch, and delete switch functions are the primitives. Maze will also analyze the primitive semantics using tent analyze and symbolic exclusion. In this example, the semantic of create router primitive is that it has 3 malloc, and all of the and each of the size of malloc is 160. The next step is to assemble this primitives and get the expected layout. Assembling primitives means that we need to know which and how many primitives are needed and what's the order of each primitives. This is very challenging. Other solutions they cost lots of time but have a very low success rate. The main reason is that there's noise in the primitive. The noise is the unwanted allocations or deallocations in primitives, and the noise brings lots of side effects. In this paper, we used a novel technique called dig and fill. First of all, we considered the layout manipulation problem. We think the heap layout manipulation is to place a target object O into a target address P. Then, if the object O did not be placed at the address P, there must be the 2 situations below. First of all, we call it the dig situation. This is that at the time of allocating the object, the target object O, the target address P is taken by another object. So we need to dig memory holes to place the unwanted object by adding the primitives that could free objects of proper size. The other situation, we call it the fill situation. This is at the time of allocating the target object O. The target address P is empty, but the object O still force into other hosts. So we need to fill these memory hosts before allocating object O by adding primitives that could allocate its objects. Based on the judgment of dig and fill situation, we can know where to insert the primitives, which is the order of how to assemble primitives. Then we need to form Diophantine equations, and by solving the equation to figure out which and how many primitives are needed. In the equation, x is the amount of each primitives, and d is the target distance of POC, and the delta d is the delta distance of each primitives. So we need to measure the distance. First of all, we need to introduce the measurement unit, which is a standard fill or dig operation. We call it standard because it only contains one allocation or deallocation, and the size equals to the size of target object O or the target address P. Then for the given POC, we will craft a pair of standard dig and fill operation and add it into the execution trace of POC until the target object O is placed into the target address P. Then if D standard dig operations are required, the target distance is positive D. If D standard fill operations are required, the target distance is negative D. In the end, we will also add each primitives into the POC's trace. If the target distance before and after inserting a primitive are D1 and D2, then the target distance of the primitive is D2 sub D1. By solving the equation, we can know that which and how many primitives are needed. In this example, we can see that the target distance of POC is positive 1, and the delta D of each primitives are positive 2, positive 3, and negative 2. By solving the equation, we can know that we need 1 create router and 2 delete switch primitives. Then based on the dig and fill algorithm, we can know the primitives orders, so we can assemble these primitives and get the expected memory layouts. And this is the overview of maze. We can see that there are mainly 2 parts in maze. One is the heap layout primitive analyze, and the other part is heap layout primitives assembly. In this part, I will introduce the evaluation results. First benchmark is the CTF benchmark. We select 23 programs from the CTF competition, and maze can hijack the control overflow for 5 of them and leak sensitive information for 1 of them, and output exploitable memory layout for 10 of them, but failed for the other 5. We also evaluated maze on real-world programs, which is PHP, Python, and Perl interpreters. For script interpreters, the layout primitives are the sentence of scripts. We can see that by assembling the such primitives, maze is much faster than other solutions and can generate the expected layout for all of them. We noted that generating expected layout is not the final working exploit. There is still a lot of things need to be done, but they are not the scope of maze. The last benchmark is the man-made benchmark. We mainly evaluated the robust of maze. First of all, you can see that the number of noise did not influence the success rate of maze, but the amount of primitives will influence the success rates. But the success rate is is still more than 87. Then MIS can also support the multi-object position constraint memory layout, which is a very complex memory layout, by generating a system of Diophantine equations. And we can see that for the multi-object position constraint layout, MIS still has a very high success rate. In the last part, we can make some conclusion. First one is that MIS can transform the layout in POC into the expected layout, and MIS is very efficient and effective, and can support the multi-object layout. Then the last part is the other challenges of AEG. We can see that MIS is only solved one problem, which is also known as heap likelihood inference. But there are still lots of other challenges needs to be done, and many of them are still very important, but there's not a very effective solution yet. That's all, and thank you. Any questions?